This video is about collision theory, which is an explanation that we have for what we see macroscopically in kinetics. Because this is a theory, just a reminder, I like to do this as often as I can, to contrast between what a law is and a theory. The difference between a law and a theory is that laws describe things. In physical science, it comes down to an equation that describes the relationship between two measurable variables. Theories, on the other hand, explain things. These are often verbal. Sometimes they're complex. They have like multiple postulates. And another thing about a theory that's important to understand is that theories are not just hunches. They're not just a guess at something. It's not accepted as a theory unless it has strong supporting evidence. So in everyday ordinary life, non-scientific people will use the word theory, and even scientific people will use the word theory as kind of a stand-in for just a hunch or a guess, or what a scientist would call a hypothesis. A theory is not called a theory until that hypothesis or that hunch has been tested, usually repeatedly, and the evidence supports it. And another thing about theories is they are not what we consider permanent or settled. They are often updated as the testing refines our understanding, or we develop more sophisticated ways to measure the things that the theory is explaining. An example of this would be Boyle's law versus kinetic molecular theory. Boyle's law, the relationship that we had between pressure and volume, that says that as the volume increases, the pressure decreases and vice versa. Before they had an explanation for that, they knew that that was true. They didn't know why, but it was just something that was described by that, again, it was a relationship. Pressure is inversely proportional to volume. But the kinetic molecular theory explains why this was true in terms of particle collisions. So the theory that we're looking at now is called collision theory, and it's an explanation of the rate laws that we see. So here's one postulate of the collision theory. The rate of reaction is going to be proportional to the number of effective collisions between particles that are reacting that happen in a certain amount of time. So the particles have to collide with each other to react, and the more of these collisions that result in products that occur in a given amount of time, well, that would be proportional to the rate. Another postulate is that particles in effective collisions are oriented in such a way so that the atoms that end up being bonded in the product collide with each other. Here's an example of what I'm talking about. If we had this reaction where two NOBr molecules are reacting to produce two NO molecules and a Br2 molecule, this would be an example of an effective collision because the two Brs have an opportunity to interact with each other and collide, and so therefore the bond could be formed, and then that would allow the two NOs to separate. This would be another example of an effective collision because the two Brs would be colliding with one another, and so this orientation would result in products being formed, and that's an effective collision. This would be an example of an ineffective collision because the particles are oriented in such a way that the Brs never actually interact with each other, and so they can't bond. Here's another postulate. Particles that result in effective collisions, even if they're oriented properly, they have to have enough kinetic energy that when they come to a stop, the orbitals in the bonding atoms are going to be overlapped sufficiently for the bonds to form. So they can't just gently nudge each other. So the collision that we see here would be an effective collision because it has enough energy for the bonds to form. But this would result in the particles just bouncing off of each other because they don't collide with enough energy to force those bromines deeply into each other's orbitals, enough for bonds to form. So as we go through the process of the reaction, there are some energetics involved. At first we have the reactants, in this case, two separate NOBr molecules. And then they come to a collision point where they actually come to a stop. And all the energy that they carried into that collision is now stored as positional energy, or what you might call potential energy, as we get this kind of deep overlap of orbitals. And then they separate into products, and that energy comes back out as kinetic energy, with some energy still stored in the positions of the particles, and sometimes that's more and sometimes that's less. That thing that we have in the middle that's not exactly reactant and not exactly product is called the activated complex and exists at high energy. So that means it's unstable. It's not going to exist for a very long period of time. One way that we can represent the energetics of this reaction graphically is if we have the positional energy, or what we call the chemical energy storage, on the vertical axis, and the horizontal axis just represents the progress through the reaction. Now this could be thought of as time, but the time frame is going to be pretty small. It's probably more useful to think about this as pure reactant at the beginning and then pure product at the end. And so this is the process through from only having reactants to only having products. So at first, we have the energy that's stored in the individual reactants. And then the activated complex has converted all the kinetic energy that those particles had into positional energy as those particles get smushed together. And then later on, we have the energy that's stored in the products. If we think about this in terms of an energy profile, the activation, the energy starts out low and goes down to a lower value, but in the middle there's this high peak of positional energy, of stored energy in the position of the particles. We call that the activation energy for the reaction. So it's the amount of energy that you have to add to reactants to get them to form that activated complex at the top of that energy hill. Here's another way of thinking about this. If we track energy positional and kinetic, not just positional energy, through reaction process, this is what the positional energy curve might look like, kind of generally. And this is what the kinetic energy curve might look like. The chemical energy store, the positional energy, is gathered from the kinetic energy as the once moving particles come to a stop in the middle here at the activated complex stage, and that's where the chemical energy store is the highest. Now, in order for this reaction to occur, the kinetic energy that is available to lose has got to be greater than or equal to the activation energy that has to be required for this activated complex to form. So you're only going to get an effective collision if the kinetic energy that the particles originally had back in this state when they were reactants is at least as big as the activation energy that they have to acquire in order for the reaction to proceed. One other feature of this graph is the difference between reactants and products. That's the enthalpy change of a reaction, and we have talked about this a little bit when we were talking about bond energies in an earlier video. In this case, the products have less positional energy stored than the reactants did, and that's what we call an exothermic reaction. It's an energy out reaction because this difference between the reactants and product energy, that goes out into the surroundings. A reaction like this would feel warm to the touch because it would be giving off that excess energy. Let's compare exothermic and endothermic reactions. We saw an exothermic reaction. This is where delta H is a negative value, and so this is an energy out reaction. That difference of energy is going to go out of the system, and therefore the surroundings would gather it and it would feel warm. This is an endothermic reaction. So this is a positive value, so that means energy is going to be going into the system from the outside. So this is a reaction that would feel cold to the surroundings. Both of them have an activation energy associated with forming that activated complex. And if your kinetic energy is big enough to get you kind of over that hump, then products will form. That's what we would call an effective collision. We have seen earlier that one of the factors that influences the reaction rate is the temperature. If the rate increases with the temperature, K must increase as well. And the reason for this is because here's your rate law. Rate is equal to K times concentration of A raised to the N power. Concentration of A and N are not going to change if the only thing that's happening is the temperature goes up. So the only way the rate can go up is if K also went up. So here's an example. If you have this reaction here where N2O is decomposing into NO2 and O2, and you do it at 5 different temperatures, these are the K values that you will find if you analyze the kinetics. We can see that as the temperature is going up from 293 to 303 to 313 and so on, the K values are getting larger and larger and larger as temperature increases. So plotting this on a graph where we have the temperature on the horizontal axis and the K value on the vertical axis, we can see that a straight line is not a good relationship. Now, if you see this upward opening parabola looking thing, thinking back to what you know about model building from science fundamentals when you were a freshman, you might think the smart thing to do here is to square all the temperature values. So if we do that, we find that that didn't really work, but that's okay because we know that a cubic relationship also has an upward opening parabola looking shape if you're only seeing that one quadrant in the positive values. So let's try cubing the t values. Once again, that was ineffective in creating a linear relationship between these two values. Well, here's another possible linearization. This is the relationship between y and x. If y is equal to e raised to some constant times x, if a is a positive number, it would have that same kind of a shape. If we take the natural log of both sides, this becomes natural log of y is equal to ax. And that would be a straight line if we plotted the natural log of y on the vertical axis and x on the horizontal axis. So if we try doing that with r values, taking the natural log of k, which was on the vertical axis, against temperature, which was on the horizontal axis, maybe we'll get a straight line. So we'll try that, natural log of k on the vertical, temperature on the horizontal. And in fact, it does kind of look like it straightened it out, but it didn't completely. In fact, if you look at these points, there is a slight curve to the data there. Now this is getting super picky, but to follow through with how this model is built, we're going to have to assume that that was a big enough deal that at high and very low temperatures, the model would be not very good. And so we have to look for another correlation. That slight curve suggests that we should take the square root of the temperature values because it kind of looks like a side opening parabola. If we try taking the square root of all the temperatures, in fact, the R value does increase, but it does not make the arc go away. It still looks kind of arced. Here's another possible linearization. If you have the relationship y equals a over x, and a is a negative number, this is the shape of your graph. It's a hyperbola, and that shape has the same appearance as a side opening parabola. And if we go back to our original plot of natural log of k versus t, we notice that these are all negative numbers here. So we are down in this lower right-hand quadrant where we would see that if this was that hyperbola. So remember, our vertical axis is now natural log of k, so this could mean that a over t, because our horizontal axis is t, might give us a straight line. So let's try that. And when we do that, we get a very good R value, which we had been getting before. But now the perception of a curve is missing. This data looks like the only reason that R isn't a perfect 1 is just due to randomness and not due to any other mathematical relationship that might possibly explain this. So the general form of this relationship would be that the natural log of k is equal to some constant, let's call it m, times 1 over t plus b, the vertical intercept. Now that constant is the slope of this line. When you develop a mathematical relationship that's linear, the vertical intercept and the slope usually have some physical meaning. And so we might want to find what that meaning is and put some more meat on the bones of this skeleton of a mathematical model that we have here. So we're going to take a slightly different approach, and this is the one that was actually used by Svante Arrhenius when he figured this out a long time ago, and try to figure out what m and b might actually be in this relationship. So thinking about temperature and rate, and thinking about the energy that particles have in their kinetic storage mode, we can get this graph where the total of all particles is the area under the curve. And so this would represent some sample of particles at some temperature. Thinking about collision theory, the activation energy is some value along the energy axis, And remember, we said that if kinetic energy was greater than or equal to the activation energy, those are the only collisions that are going to result in effective collisions that will actually produce products. So the area under the curve that's to the right of the activation energy line, those are the only particles that are going to be able to do effective collisions. And since rate is proportional to the number of effective collisions per unit of time, the rate is also going to be proportional to the shaded area that we have here. Now, if we increase the temperature, some particles are always not moving because those are the ones that are in mid-collision. So that has to stretch the graph out because the average moves to the right. And that means that it has to flatten the graph out as well. Now the shaded area that's above activation energy is bigger. And since the rate is proportional to the shaded area and the shaded area got bigger, that means the rate would have to increase with higher temperature. So that means that the rate is proportional to the shaded area. So that means that the K value is also proportional to the shaded area because remember, rate has to be proportional to K here because the concentrations are not changing when all you change is temperature. So here we're going to have to do a little bit of magic. It's not really magic. It's just doing a tricky integration that I don't want you to have to get lost trying to follow. If you are into calculus and you understand what integration is and you're curious about this, talk to me and I can explain where this comes from. But it turns out that if you use some statistical methodology, the shaded area in this graph is going to be proportional to E raised to the minus EA over R, that's the universal gas constant, times the absolute temperature. And since K is proportional to the shaded area, that means K is proportional to E raised to the minus EA over RT. That's the activation energy divided by R times T. So to change this proportionality into an equation, let's add a constant of proportionality here named A, and this is called the frequency factor. And the reason that it's called the frequency factor is because Arrhenius recognized that orientation was the other factor that would have something to do with reaction rate besides temperature, just besides how much kinetic energy the particles had. So the frequency of particles with the proper orientation for a particular reaction would have to be related to this constant of proportionality, he thought. So he gave this the name frequency factor. So if we turn that into an equation by just inserting this frequency factor, we get this. Now, if we take the natural log of both sides, we get another form of the Arrhenius equation, which is what this is called. And that would be the natural log of K is equal to the natural log of A plus minus EA over RT, if you're following the rules for logs. So what that's telling us is that the slope that we saw in that general natural log K equals M times 1 over T plus B, that's actually the ratio of the activation energy to the universal gas constant R. And the B from our general equation, well, that's the natural log of the frequency factor. Where this is really useful is if we can create a two-point form of the Arrhenius equation. So what we're looking at is just taking two different temperatures and two different Ks and subtracting one from the other. So let's say we have natural log of K1 at temperature 1, and then we have natural log of K2, that's going to be minus EA over R times 1 over the second temperature plus the natural log of the frequency factor. And if I take this top reaction and subtract the second reaction, I'll get the natural log of K1 minus the natural log of K2 is minus EA over R times 1 over T1 minus 1 over T2. And the natural log of A just drops out of there, and so we never have to actually know what the frequency factor is. We could rewrite this as natural log of K1 over K2 by the rules of logs is minus EA over R times 1 over T1 minus 1 over T2. So let's use this in an example problem. At 25 degrees C, the rate constant for reaction is given. The activation energy is also given. We want to know what's the rate constant at 75 degrees C. Well, first of all, 25 degrees C is 298 kelvins, and we have to use absolute temperatures here. 75 Well, that's 348 kelvins. So the natural log of K1, let's call it, 2.0 times 10 to the third per seconds, minus the natural log of K2, which is our unknown, is going to be equal to 15,000 joules, and I'm writing it as joules to keep it consistent with the values, the units of R, which is 8.314 joules per mole Kelvin, 8.314, times 1 over T1, 298 kelvins, minus 1 over 348 kelvins, that was T2. So that means the natural log of K2, if we evaluate this, is 7.60 minus 0.870, which ends up being 8.47. So K2 is equal to E to the 8.47, which is 4.8 times 10 to the third, and it's per second because that's what the unit of K was originally. Let's try another one. Chemists use this rule of thumb that every 10 Ks of temperature increase roughly doubles the rate of the reaction. So we want to find out what activation energy would make that true for an increase from 25 to 35 degrees C. So let's say that we have doubled the rate. That means we've doubled the K. So that means K1, if it was 1, K2 would be 2. That equals to minus EA, which is our unknown, over R, 8.314 joules per mole Kelvin, times 1 over T1 minus 1 over T2. But this is 298 kelvins, remember, and that would make this 308 kelvins. So that's what we're putting in here. 1 over 298 K. That's 1 over 308 kelvins. So that means 8.314 joules per mole Kelvin times the natural log of 1 over 2 equals minus EA times 1.09 times 10 to the negative fourth inverse kelvins. So negative 5.76 joules per mole Kelvin is minus EA times 1.09 times 10 to the negative fourth per kelvins. So when we solve for EA, we get 52,800 joules per mole, which would be 52.8 kilojoules per mole.